Welcome back to Basic Biostatistics 2 and to the second last module, which is module 9, which is all about logistic regression analysis. In this module, I'm going to show you how to run logistic regression analysis in SPSS and how to interpret the results of the analysis. Logistic regression analysis is a model as linear regression analysis, but not considering that the association or correlation is linear. That's why it's logistic regression. For the exact theory of the model, I refer you to the theoretical part of the course or to any other course you have done prior to this course. In logistic regression analysis, the outcome variable or the dependent variable, the one we try to predict, is dichotomous, which means it's a categorical variable consisting of two categories only. The independent variable can be continuous, can be categorical, they don't have to be normally distributed, and they can have more than two categories without any problem. Logistic regression analysis, they will give you odds ratios in the end, a 95% confidence interval of odds ratio. An odds ratio of 1 means that there's no risk increase nor risk decrease. An odds ratio of more than 1 means that there's a risk increase, and an odds ratio less than 1 means that there's a risk decrease. Please try to go back to the theory and read something about the odds ratio in order to get familiar with the concept. Good. Where to find logistic regression analysis? We go to Analyze and to Regression, where you find all the regression models. Here we find binary logistic. It's binary because the outcome variable or dependent variable is dichotomous, consisting of two options. Now in this exercise we try to predict the odds in having back pain. We'd like to know, for instance, for increase in body weight, what's the odds of having back pain, or for increasing any other factor, for instance smoking, if this increases the odds ratio of having back pain, maybe due to some biological or physiological mechanisms. The dependent variable is back pain, so we select back pain as a categorical dichotomous variable into dependent variable list, and we choose smoking status, the categorical variable, as one of the covariates, and we choose weight of the dwarfs as the continuous variable as covariate. Before we can run the model, we have to tell the system or the program some information. For instance, we have to tell him which of the variables, independent variables or covariates, are categorical. We click in categorical, and the only variable that is categorical is smoking status. We click in smoking status and we move it into the categorical covariates window. If we calculate the odds, we need to know the odds compared to what? What is the reference category? In this case, I always choose the reference category as the first one. At the moment it's programmed as the last one, which would mean smokers. Remember that 1 is coded as non-smokers and 2 is coded as smokers. I would like to have as a reference category the first one, which is non-smokers. That's why I click on first, I click on change, and now you see that in categorical variable it says smoking indicator first. This means what will be the odds, or how much will change the risk of back pain by increasing from category 1 to category 2 in smoking, which means from changing from non-smoking to smoking. Changing from non-smoking to smoking, what are the odds in having back pain? This is what we will get from this. We click on continue. We go to options. In options we choose the Hessman limit of goodness of fit of the model test, and we choose the confidence interval for the odds ratio. In logistic regression models we can establish how well the model is, or the goodness of fit, by knowing the Hessman limit of test result. We click on continue and we can click on OK, and the program will calculate all the tables needed for logistic regression analysis. Let's go through the tables one by one. The first table is a case processing summary. It tells us how many cases are included in the analysis. As usual, 60 cases, non-missing cases. The second table, the dependent variable encoding, tells us that the outcome variable no and yes, having back pain yes and no. The third table tells us that about the categorical variable, the smoking. So non-smokers are 30, we have 30 smokers. This is all descriptives. And then we're gonna get the first results of the logistic regression analysis. Logistic regression analysis works with blocks. It starts with the first block with the first set of variables, which only includes the constant in the regression model. It tells us without knowing the smoking status or the weight, how much the constant alone can predict the outcome variable, which will be back pain. This means that it makes a cross table. We have 32 dwarfs that have no back pain, and we predicted as 0 have not back pain. We have 28 dwarfs that have back pain. It basically means that we have a 50-50 possibility for predicting if a dwarf has back pain based on a constant, because they have back pain or they don't have. It's more or less a 50%. It's a little bit more. It's about 53%. However, if you check the step 0, that only the constant in the model, the constant is not statistically significant. This means that the constant alone in the logistic regression model cannot predict whether you have back pain or not. This makes some sense, and in almost all of the cases, this is the result you should get. Because if you can predict, if you can guess if someone has back pain, you don't need a logistic regression model. It gives us in the next table a summary of variables that are not in the equation. We know that weight was not in is still not in the model, and smoking has not yet been included, as the model consists only of the constant. Good. The next step is the program adds smoking and weight as one block, both variables at the same time, into the model we have defined. So we have an omnibus test of coefficient, which means that adding these two variables in the model changes significantly. Basically what logistic regression does, it calculates your sort of a chi-square test, calculating whether adding two variables or one variable will change in the model. And it certainly does in this case. The next step is it gives you a Cox and Snell R-squared test result and a Nagelkerke R-squared test result. This basically tells you how complete the model is, as in R-square values we had in previous multiple linear regression models. In this case, you can select if you choose the Cox and Snell R-square value or if you choose the Nagelkerke R-square value. For instance, if you're going to run other models, you'd like to compare where the completeness improves. So if you choose Nagelkerke R-square of this model, you compare it with the Nagelkerke R-square of the next model you're going to run. This is about a 30% completeness, which is not too bad. The next table shows you about the goodness of fit of the logistic regression model. In that case, the Hosmer-Lemeshoff test gives us a p-value of 0.483. If the p-value is bigger than 0.05, this means that it's a good model that has a good goodness of fit. In that case, we have a good model because the p-value is 0.483. Further, we have the contingency table for the Hosmer-Lemeshoff test we can omit, and the classification table, which tells us now, knowing smoking status, knowing the weight of the dwarfs, how well can we predict if someone has back pain or not. The percentage correct, overall percentage 70.17%, which means that if you know the back pain and the weight of the dwarfs, we can predict correctly 72% of who has back pain and who doesn't. The odds ratio finally can be found in the variables of the equation, where we have the B of smoking minus 201, but more important, the program calculates directly the odds ratio, which are found in XB. These are the odds ratio and the p-value to each odds ratio. For instance, smoking is statistically significantly can predict the outcome variable, which is back pain. The odds ratio is 0.134. This means it's a reduction in risk. As you have coded like the reference value is non-smoking, this means if you're changing from non-smoking to smoking, increasing the category by 1, the risk of back pain decreases. This is weird for dwarfs, but you have to know that there's no real information about the physiology of dwarfs. It seems that smoking protects the dwarfs from back pain. Maybe we can hypothesize this because if they go out and have a smoke, because they can't smoke indoors, have more physical activity, and due to some mechanism, back pain decreases. We have the 95% confidence interval for the odds ratio, which ranges from 0.0349 to 0.462. What about weight? Weight is as well a predictor, a statistically significant predictor of back pain with a p-value of 0.033, less than 0.05, and the odds ratio is 1.114. This means if weight increases by 1 unit, the risk of back pain increases by 1.11 times, which is an 11% increase for 1 unit increase in weight. Weight has been measured in kilogram. This means that if we increase the weight of the dwarfs by 1 kilo, the risk of having back pain increased by 11%. And finally, we have the 95% confidence interval for that odds ratio. This is all I want to tell you about odds ratio and about logistic regression model. Now have a look once again at this class. Try to do some logistic regression analysis of the database, interpret the results, and once you're comfortable with it, please do the quiz and the exercise and try to complete the task before deadline. I hope you have a great day, and I'll see you in the last module, module 10, which will be about survival analysis. Thank you very much.